Good afternoon, everyone, and welcome to our third and Lunch and Learn webinar in the webinar series, where you will discover more how to predict and manage heat issues in your electronics application. But let me introduce myself first. My name is Tisa Sitar. I'm a marketing officer at Infinite Simulation Systems and a moderator of this webinar. But before we start, I would kindly ask if we can wait 1 or 2 more minutes for everyone else to join, and then we will proceed further. So please just a minute or two and we continue. Okay, so let's begin. First, a quick instructions on the GoToWebinar tool you're currently using. As you can see, you have few different options. You can minimize or maximize menu. You can switch to a full screen mode. Everyone is muted and you cannot unmute yourself, but of course you're more than welcome to ask questions. Just in that case, please do not raise your hand or trying to unmute, but just write the question down under the question tab that you see. And all the questions are going to be answered at the end of this webinar. Please also note that the webinar is being recorded, but the recording will be sent to you together with the presentation slides to around 2 days after this event. So today I'm joined by my colleague, application engineer Odysseas Votsis, who will tell you more about how to use Ansys simulation tools to predict and manage heat issues in your electronics application. But let's first look at the agenda. So I'm gonna give you a very short introduction on Infinite Simulation Systems for those that might not know us yet and are the first time with us. And then I'll go give my words to Odysseas, who will be the main speaker. So, Infinite Simulation Systems, we are Ansys Elite Channel Partner for the Benelux region, being active in computer-aided engineering for more than 30 years now. We are located in the Netherlands in a small city called Breda. You can also see our office on the picture. And when we talk about broad product portfolio, we basically mean that we are not active only in electronics, but also in many other domains like mechanics, fluids, optics, photonics, and more. Besides Ansys simulation, solutions are applicable across various industries and applications. Our main goal is to improve your design efficiency, of course, but distribution of the simulation software is not the only thing we do. We also provide consultancy and support. And last but not least, we organize trainings, theoretical and practical ones, where you can really learn how to use these Ansys tools. And everything I just mentioned, you can check and read more about on our new website. It was launched 3 months ago. So if you're interested, please feel free, scan the QR code and read more about it, or check our upcoming events and so on. So please feel free to scan it. But now I'm gonna give my words to Odysseas, and I wish everyone to enjoy the presentation.
Thank you very much, Tisa, for the intro. I will be going now through my presentation. We are here to talk on this, once again, this lunch webinar, hopefully making your lunch a little bit tastier. We know that traditionally businesses have just used the design, build, test, break, fix cycle. However, such an approach can be expensive and time consuming. Further, design rules and best practices may not provide engineers with enough guidance to properly design modern, cutting-edge products. By using simulation, virtual models and prototypes can be created and simulated, giving engineers more freedom via virtual testing. This will help engineers to have a better insight of their design, but also give a higher degree of confidence that the physical tests they will run in the future will be successful. If simulation is used as a design tool early in the development process, it can greatly benefit and cut costs. Here in the graph, we can see that with the traditional approach, the problems can only be detected when there is an actual prototype. And to resolve them in this stage, it can be 100-fold more costly, both in terms of money, but also in terms of time. If problems arise even later in the development phase, the costs increase exponentially. Working with simulation tools early in the design process, engineers can predict issues and work on solutions or changes very quickly without the need of physical testing. This also seals out problems that might occur very late in the development, which will be detrimental in costs. Now let's talk a little bit about electronics design challenges. Engineers, as we know, must address a wide variety of design requirements when designing electronic systems. These range from electrical, such as signal and power integrity, thermal, such as the implementation of optimal cooling strategies, or mechanical, the ability to withstand the thermal cycling, shock, vibration, drops, etc. Furthermore, products are expected to intended and function as intended for at least a specified amount of time. Engineers also need to consider the effects of manufacturing, transportation, and product operation as part of their design process nowadays to ensure a viable and a good product. So these challenges are very difficult, and the need of simulation is getting more and more. Ansys provides a suite of tools and workflow solutions that address this wide range of electronic reliability concerns. Each aspect, electrical, thermal, mechanical, and reliability and lifetime predictions, plays a key role in the understanding of how electronic systems, operate and perform in a variety of applications. In this webinar series, now we are in the third webinar, we're going to give focus on these elements. We started with signal and power integrity, and then we moved on to EMI, EMC concerns. You can also ask us for these webinars if you don't have them already. And today we will be talking about thermal reliability. And in our last webinar, we will be talking about lifetime predictions. So let's go ahead and see a little bit of the thermal challenges. Today we use a lot of electronics, cell phones, computers, iPads, a lot of electronics in a lot of different tools and applications. Currents flowing from one direction to the other causes elevation in heat, and that's where the problem happens for us. Most important problem is electromigration, which is the process of the heat breaking up atoms from the structure and causing them to move. This leads to both shorts and opens in the circuitry. Heat can also cause a lot of mechanical failures. A lot of material properties will change with excessive heat, thus worsening the operation robustness or the efficiency of the product itself. In some scenarios, we can even have catastrophic failures with vias and traces burning out on PCBs or different components burning or having very high heat. So more specifically looking at the PCBs, the thermal expansion coefficient changing with the rise and fall of the heat causes a very big solder joint fatigue. So during the temperature cycling, a solder connection expands and contracts, which after many consecutive cycles can cause degradation of the connection and thus failure of it. This lifetime behavior can also be predicted, and we will be talking in our last seminar about this lifetime behavior. Today we'll be talking more about heat. This thermal cycling was a very big issue with Microsoft gaming console, the first gaming console, Xbox 360, and it led to a whopping of 40% failure rate for the first model iteration. You can understand that the costs for this are immeasurable, so it was better to catch it early than to ship a product with this much problems. We know also that we know also that with rising temperature, we have PN junctions decrease their forward voltage. So the transistors in a PCB are not working as intended. All these reasons have caused thermal reliability and thermal management to become a bigger and bigger topic in electronics in the past years. However, we do know that still today, companies are leaving thermal reliability as a last step, which should not be the case. And when we are talking about electronics, there are different scales. We can focus on the chip level, on package level, PCB level, or complete system level, or even complete rooms, such as server rooms and data centers. And for all of these different scales, we can perform thermal simulations on them. And that is what we are going to see also today. Maintaining thermal integrity is an essential part of designing best-in-class electronic systems. Thermal simulations allow engineers to evaluate and optimize cooling strategies. For example, forced convection approaches using fans versus natural heat lowering conventions. Or even we can help with component design, such as designing of a full heatsink. Using simulation tools, users can evaluate thermal performance from the chip or a die level all the way up to the data center level, as we talked about. Users can also consider downstream effects, such as thermal mechanical effects, like PCB warpage or stress on the PCB itself. So let's take a closer look at the simulation tool that Ansys has for the thermal reliability analysis. So the tool is called IcePack. IcePack is a solver for thermal management. It does a finite element analysis of the airflow or the heat transfer of the convection. So there is a flow of fields, and we are then solving the Navier-Stokes equations within this field. It can simulate both steady state and transient analysis as well. There is also a very big database with components coming from manufacturers themselves, such as heat sinks, fans, etc. This is, of course, to make our life easier. Lastly, it has capabilities of reduced order modeling, as well as coupling with other physics solvers, which I will touch upon later a bit. So in terms of the fidelity of the tool, it's up to us how much effort and time we want to put in our analysis. If we want to do a quick and dirty analysis, we can have some primitive object with simple shapes and maybe even 2D components instead of 3D. So as the top left pictures shows. In the top left picture, the model is very simple and it can run very, very fast, of course. Once we have finalized the basic thermal design, we can maybe import some ECAD files and start having more detailed 3D shapes. So in the middle picture here on the right, we have the PCB board with detailed traces, 3D fans, and a very detailed heatsink. And then we can run an analysis that will give more insight and accuracy of the real world. And lastly, we can even import mechanical CAD designs for a far detailed analysis and a very high level of fidelity. This, of course, will take more time to simulate, but it will give us also the most accurate results. So those fidelity steps helps us tailor the design, the time and the effort that we need to do in order to solve the problem. And this is, of course, tailored depending on our effort, our needs, and our workflows. Now let's take a look at this, how thermal simulations can help on these different scales that we talked about. So when it comes to the package, it's important to provide characterization of the thermal aspects of the package and its different components in detail, so we can have a good understanding of how the package will perform. We can efficiently extract the thermal circuit of the package as a Delphi model So we can describe the chip performances as a single object, and then we can quickly get to know its thermal interaction with the environment. If we move on the higher level and go to the PCB, which will include packages, resistor, capacitor, via, traces, and of course other components as well. We can have then a layer by layer approach and analysis and see how the conductivity map of the PCB traces can have high and accurate heat distribution on our board. And we can see this heat distribution layer by layer. But of course, since IcePack is a full 3D CFD solver, we can see also how this thermal distribution is interacting with the environment itself and the air around it. So in this case, we can have what-if scenarios and investigate how to cool the board using maybe different strategies. Maybe we can just switch some component and then we will have a better thermal behavior. Or by separating some components, we can have a better thermal map. But of course, we can also do a what-if scenario of different heat sinks. Maybe we have two different manufacturers and two different heat sinks, and we want to see which is better for our design. Or we can even have a different what-if scenario of the different position of the cool fans that we might be using to cool our system off. So you can see that we can play a lot around in this 3D environment of IcePack. Of course, also there is a very smooth coupling between the thermal and electrical analysis, and I will be discussing this a little bit later. So in the entire electronic system level, we might be having different PCBs, we might be having heat sinks, different shieldings, motors inside, etc. A complete system can be very complicated, and it's crucial that we understand the full system thermal behavior. Ansys IcePack can take a variety of both mechanical CAD and electrical CAD designs, and we can include both of them for the thermal simulations that we will be doing. So we can have a very detailed mechanical model and its electrical characteristics within IcePack to simulate. This way, we can study easily large and complex systems such as motors, projectors, drones, smartwatches, as you can see here in all of these pictures. Another way to talk about thermal management and thermal reliability is a dynamic thermal load, which changes a lot with today's leaps of technology. As you know, when you're using your cell phone for maybe only a call, it's not getting too hot, but then you're also putting some music on, you're also watching a video on YouTube, you're also using the Google Maps, so your GPS. So there is a lot of power variation coming from the applications that you use in your mobile phone. This change of power basically means a change of temperature. So it's important to investigate the effect of this dynamic change of the load temperature in the whole system over time. This whole process makes it more challenging for the engineer to have accurate thermal reliability. So simulation can help tremendously on these very difficult cases, and that comes with today's technologies and them being much more sophisticated. Finally, let's briefly talk about the coupling of IcePack with other physics solvers. IcePack, while being a very powerful CFD solver, has a very good connection with other Ansys tools as well. It generates the thermal network on the chip level. It can import the electrical and ohmic losses from different electromagnetic simulation tools such as HFSS and SI-Wave. Once it generates the thermal maps, it can also send to Ansys Mechanical or generate a reduced order model to be used with system tools such as Ansys Twin Builder, or even third-party network tools such as MATLAB or Simulink. IcePack has coupling towards the finite element methods tool, electromagnetic tools, and CFD tools, and eventually passes results to the system-level connections for system response. There is a comprehensive multi-physics analysis between all of these tools that works seamlessly. So let's look at an example here of the two coupling between IcePack and SI-Wave. We talked about SI-Wave in our first webinar, So if you want that, please let us know. SI Wave with its solvers will analyze the PCB and calculate the ohmic losses and the power losses, and then it exports them over to IcePack. IcePack will then use this data to finally calculate temperatures and then sends back temperature maps to SI Wave. These temperatures, of course, will modify the power losses of the board, and then the power losses are sent back to IcePack. So we have this loop between the two softwares in order to finely tune everything uh, and be exact and accurate about our predictions. In this loop, we can have a specified convergence criteria that once is satisfied, then this means that we have our solution. And once we have converged this thermal solution, we can have the thermal distribution and expansion details along with the electrical components and the electrical behavior of our system. And then we can further investigate mechanical aspects of the PCB, such as possible thermal stress of the PCB or mechanical deformations due to heat. We can even see the effect of the heat to the solder balls of the board. So as you can see, IcePack with its coupling, we can have a fully electronic, thermal, and mechanical simulation of our whole entire system. So we can be very sure what to expect. So to summarize, when we talk about thermal reliability, we want to make sure that we have accurate thermal models. We have all the details in the system. This is including the mechanical CAD and the electrical CAD. The material properties are also very essential to properly define. We need to understand how much detail our models should have, because thermal reliability can be measured at any scale, from chip to the whole system. This can seem troublesome. However, with Ansys IcePack, efficiency and ease of use are on the highest level. So simulation and Ansys IcePack can really help us dig deep into our system and really simulate the thermal behavior of it. Thank you very much for your time. I will give back the microphone to Tisa.
Thank you, Odi. So before we proceed with the questions, I would just like to quickly share some contact details with you. So in case of any additional questions that come after the webinar, or you want additional information, please feel free to contact us. You do not have to write all this information down because the presentation will be sent to you after anyway. Okay, moving to the questions. We received 2 questions. So Odysseas, I would start with the first one, which is asking, if you want to test the effect of different heat sinks, can you also change the material of the heat sink and compare the results?
Yeah. This is very easy to do with IcePack. You have, as I said, you have your electrical or your mechanical design imported to IcePack, but also IcePack has a built-in tool to change also certain parts of certain geometry aspects. However, also you can change the specifications or the material properties of each and every different component in your system. So you might have a sink that is, I don't know, copper, and then you say, okay, I want to change this copper to aluminum. This can be done with basically 2 clicks. And of course, there are also optimization tools within IcePack itself. So you can run an optimetrics analysis with different types of criteria that you want. So I don't know, maybe you want to see different sizes of heat sinks. So you can just run an analysis for a 5-centimeter heat sink, a 7-centimeter heat sink, a 10-centimeter heat sink very easily and very fast.
Okay, thank you. And then the second question, is it possible to have co-simulation of both thermal reliability as well as lifetime predictions?
Yes, and I will be talking about this a little bit more on our last seminar. There is As we talked here, we saw that we can have a co-simulation of electrical, thermal, and mechanical physics. However, once we can also extend this, let's say, to a lifetime prediction with another tool of Ansys that I will be talking in our last seminar.
Okay. Well, thank you, Odysseas. These were all the questions. So we are at the end of this webinar. Uh, as mentioned, slides and the recording will be sent to you, but if you have any other questions, something wasn't clear, feel free to ask and let us know how can we help. And hopefully we see you in 2 weeks in our last webinar on electronics reliability. So thank you for your time. Thank you for
Thanks,
joining.
everybody.
And yeah, I wish you a great day. Bye bye.
Bye bye.